Right now, deep in the Pacific Ocean, there is a massive, I mean, just a genuinely massive subterranean reservoir of hot water.
Oh, yeah. A huge pool of it.
Right, and it's moving east so fast that meteorologists are actually comparing the temperature charts to a rocket launch.
Which is not a comparison they make lightly.
You know, definitely not. And basically, the weather as we know it is about to completely flip.
Yeah, because when the Pacific Ocean decides to rewrite the rules, the entire global climate system, it really has no choice but to follow along.
From the rain over your house to the wind steering hurricanes across the Atlantic.
Exactly. Everything is connected.
So welcome to today's deep dive. Our mission today is to cut through all the doom scrolling, the apocalyptic social media headlines, and decode what is actually happening with the global climate right now.
Because there is a lot of noise out there.
So much noise. We are sitting here in May 2026. The data is pouring in, and, well, there's just a lot to make sense of.
There really is.
Yeah.
The shift we're seeing right now is making veteran atmospheric physicists sit up and take very, very careful notes.
And to get to the bottom of it, we've pulled a stack of the latest, most credible official sources.
The real hard data.
Right. We're looking at current reports and raw data from the National Oceanic and Atmospheric Administration, NOAA, and the World Meteorological Organization, the WMO.
Both heavy hitters in the climate world.
Absolutely. We're also weaving in critical regional updates from DOST Pagasa, which is the Philippine Atmospheric, Geophysical, and Astronomical Services Administration.
They've got some vital on-the-ground perspectives for the Western Pacific.
Yeah, and we're pairing all that with a comprehensive internal meteorological document that details the specific mechanics of this current El Niño phenomenon.
I mean, it's a mountain of data. But when you lay it all out, a very clear, very striking picture emerges about what the next 12 months are going to look like for you.
Well, let's unpack this, because the central drama happening right now is that the tropical Pacific is rapidly shifting gears out of a neutral phase.
Right, neutral is over.
And it is creating massive buzz. Reading through these meteorological documents, it's like someone reversed the treadmill that the ocean normally runs on.
That is honestly a perfect way to visualize it. I like that, the treadmill analogy.
Well, thanks. It just seemed like the easiest way to picture it.
No, it works perfectly.
Yeah.
Because to understand what's happening today, you have to look at the normal mechanics of the Pacific, right?
Right.
Under typical conditions, you have these incredibly steady trade winds. They blow consistently from east to west.
Just constantly pushing.
Constantly. Because of the Earth's rotation and, the way that the sun heats the equator, these winds act almost like a physical plow.
Oh, okay.
Yeah, they continuously sweep and push this massive pool of very warm, sun-heated surface water all the way to the western side of the Pacific.
Boxing it up.
Exactly, boxing it up right near Asia and Australia.
So, under normal conditions, the treadmill runs east to west, piling all the hot water into one corner of the globe.
Correct. But right now, we are seeing a series of incredibly powerful westerly wind bursts near the equator.
So the winds are blowing the wrong way.
Exactly. These winds have completely reversed direction. That oceanic treadmill just abruptly changed gears.
Wow.
Yeah, so instead of keeping that warm water boxed up in the west, these reversed winds are taking that massive subterranean reservoir of hot water and sloshing it eastward.
Just pushing it all straight toward the coast of South America.
Right across the Pacific. And it's a huge volume of water.
And looking at the graphs in these sources, I mean, this isn't a slow, gentle drift.
Not at all.
The forecast models for the sea surface temperatures in the Central Pacific, what the agencies call the Nino 3.4 region.
Yeah, the key monitoring zone.
Right. Those models don't look like a gradual warming trend. The curve goes almost straight up.
Which is terrifying if you're a meteorologist. The official terminology popping up in the scientific community is an Artemis liftoff plume.
Artemis liftoff. Like the rocket.
Like the rocket. The trajectory is literally that steep.
That's intense.
It really is. There's broad consensus across nearly every major global climate agency that sea surface temperatures in this central region are locked into a path that will comfortably clear the 1.5 degrees Celsius threshold.
That's above the historical average, right?
Right, above the historical average.
And just to establish the scale here for the listener, clearing 1.5 degrees puts it firmly in the strong category for an El Niño event.
Firmly strong. But what's causing the real alarm and, generating all those wild headlines we mentioned earlier is the extreme models.
The ones predicting a much bigger spike.
Exactly. Some of the more extreme computer models are projecting temperature anomalies soaring past 2.0 degrees or even 3.0 degrees Celsius by the time this peaks in the winter.
Okay, so if you're scrolling social media right now, you're seeing the phrase super El Nino plastered everywhere.
Oh, absolutely everywhere.
People are treating those extreme models as gospel. But looking at the actual science, I have to ask, is a super El Nino a guaranteed reality, or is this just clickbait designed to make us panic?
Well, what's fascinating here is how meticulously you have to separate the atmospheric reality
Yeah.
from the internet hype.
Right, separating the signal from the noise.
Exactly. Let's start with the undisputed hard data. Atmospheric scientists tracking that subterranean heat wave have noted something very specific.
Which is?
The water moving east right now is actually about half a degree warmer than it was at this exact same point in the year back in 1997.
And 1997 is the benchmark because it was the precursor to one of the most severe, destructive El Nino events of the entire 20th century.
Yes, the 97 event was devastating. And when we're talking about the ocean, heating a volume of water that massive by an extra half degree,
It takes a lot of energy.
an astronomical, almost incomprehensible amount of thermal energy. So the baseline risk is very, very real.
Okay, so the agencies are taking this seriously.
Definitely. DOS Pagasa has already triggered active warnings because they calculate a 79% chance of an event hitting their specific region.
Wow, 79%.
Yeah, and globally, the consensus models show an 82% chance that it officially emerges between May and July.
And looking ahead to the winter?
A staggering 96% chance that it completely dominates the global weather pattern through the winter of 2026 into 2027.
Okay, so the event itself is definitely happening. The treadmill has reversed.
No doubt about that.
But what about those specific models predicting a 3.0 degree record-shattering anomaly? The super El Nino stuff.
That's where the clickbait diverges from the meteorology. Forecasters are currently battling a phenomenon called the spring predictability barrier.
Okay, yes, I saw that term repeatedly in the NOAA reports. What exactly is a predictability barrier?
It's kind of a blind spot.
Right, why is spring a blind spot for these supercomputers?
It comes down to how the ocean and the atmosphere communicate. Spring is a transitional season.
Okay.
The natural temperature gradients across the globe are weaker during the spring, which means the normal trade winds are naturally weaker.
Because everything's just kind of shifting.
Exactly. Because the winds are sluggish, the ocean and the atmosphere aren't strongly coupled together. The glue holding the weather patterns together is temporarily loose.
So the computer models are trying to read a signal, but the signal is just full of static.
That's exactly it. When computer models try to predict ocean temperatures during this loose spring transition, they have a strong tendency to overcorrect.
They see a tiny blip and freak out.
Yeah, they see a small anomaly, and because the stabilizing forces are weak, the model extrapolates wildly.
Okay, making it seem worse than it might be.
Right. They often predict surface temperatures that are far hotter and more extreme than what actually manifests by winter once the atmosphere and ocean finally lock back into sync.
So those extreme models showing a 3.0 degree Artemis liftoff, those might just be the computers getting a little too aggressive during this seasonal blind spot.
The official scientific agencies are being very, very careful about this. None of them are formally calling it a super El Nino yet.
They're holding back.
Yeah. NOAA currently places the probability of a very strong event at about 37%.
Okay, 37% isn't 100%.
No, it's not. Now, on the flip side, there are independent atmospheric physicists who argue the underlying energy is so high, there's a 50% chance this becomes the strongest event ever recorded.
A literal coin flip.
Exactly. But a 37% or even a 50% chance is not a guarantee.
Okay, that makes complete sense. It's a serious event, but the apocalyptic peak isn't locked in yet.
Right.
However, reading through these sources, even if it just turns out to be a moderate El Nino, there is a much broader context here that really changes the math.
A huge context.
Because even if the El Nino itself isn't a record breaker, the starting line has moved.
Yes.
It's like turning on your oven's broiler when the kitchen is already sitting at 450 degrees.
That is the absolute crux of the issue. I love that broiler analogy, by the way.
It's terrifying, but it fits.
It really does. What makes this specific cycle genuinely unprecedented isn't just the size of the wave coming across the Pacific.
It's what the wave is crashing into.
Exactly. It's the thermal state of the ocean it is landing in. The global baseline has fundamentally changed.
Right, because looking at the WMO data, they point out that global baseline temperatures are currently hovering around 1.4 degrees Celsius above pre-industrial levels.
Yes. And the WMO also noted back in late 2023 that greenhouse gas concentrations had hit record highs again.
It just keeps compounding.
It does. The One Planet Polar Summit recently sounded massive alarms over the accelerating speed at which the cryosphere, our global snow, ice, and glaciers, is melting.
I also noticed in the documents that NOAA just restored full access to its Mauna Loa observatory.
Oh, yeah, which is huge for data collection.
That's essentially the gold standard for atmospheric tracking.
Absolutely, the gold standard.
Because it's perched at a high altitude in the middle of the Pacific, totally isolated from local pollution, taking pristine air samples.
Right.
So we have all these world-class instruments pointing at the baseline, and they all confirm the baseline is historically incredibly hot.
Hotter than it's ever been.
So why does layering an El Niño on top of that matter so much? Like, what is the actual physical mechanism happening here?
It's because of how an El Niño processes heat.
Okay.
When that oceanic treadmill reverses and pushes all that hot water eastward, it doesn't just stay trapped in the ocean.
It goes somewhere.
Yeah, an El Niño acts as a planetary release valve. As that massive pool of warm water spreads out across the surface of the central and eastern Pacific, it releases tremendous amounts of latent heat directly into the atmosphere.
So the ocean is basically exhaling decades of stored thermal energy into the air all at once.
Precisely. Layering a potentially strong El Niño onto a global ocean baseline that is already this hot is completely uncharted territory.
Because it's never happened before.
Never. It threatens to supercharge global air temperatures and break absolute historical records worldwide by 2027.
Wow.
We have simply never experienced an El Niño in a world this warm.
So if the planet is essentially running a fever and the Pacific is acting as the heater, what does that actually look like on the ground?
That's the big question.
Like, how does a bunch of hot water sloshing around near the equator physically alter the weather outside your window?
It all comes down to the global jet streams.
The wind's way up high.
Right. These are the high-altitude, fast-moving rivers of air that steer our weather systems across the continents.
Okay.
The massive column of rising hot air generated by the El Niño completely displaces these jet streams.
It shoves them out of the way.
Exactly. And the world essentially gets split into dramatic extremes of too wet and too dry.
Okay, let's map this out geographically so the listener can picture it.
Sure.
If the hot water used to be boxed up near Southeast Asia and Australia, and now it's moving east, what happens to the Western Pacific?
Normally, Southeast Asia and Australia get abundant rain because that boxed up warm water creates constant evaporation.
Which means rising air and storm activity.
Right. But because the hot water is moving towards South America, that massive engine of rising moisture shifts entirely away from them.
Oh, wow. So they don't just lose the heat, they lose the atmospheric mechanism that actually creates their rain clouds.
Exactly. The moisture gets pulled east. This leaves Southeast Asia and Australia facing severe drought, heavily delayed monsoons, and a highly elevated fire risk. And all that moisture heads straight toward the Americas. Yes. For the west coast of the Americas and the southern United States, the El Niño forces the Pacific jet stream to stretch much further east and dip aggressively south.
Steering the storms right at them.
Exactly. It steers a constant, unrelenting conveyor belt of storms directly into these regions.
So they get hammered.
You're looking at heavy, sustained winter rainfall, significantly increased flood risks, and actually cooler than average winter temperatures in those specific bands.
Wait, cooler temperatures? I thought the planet was running a fever.
It is, but in those specific areas, it's cooler simply because of the constant cloud cover blocking the sun.
Oh, that makes sense. Just a blanket of clouds all winter.
Yeah, and NOAA had a very specific warning for coastal communities in these areas. They called it a double whammy.
A double whammy of what?
Because the ocean is generally warmer, sea levels naturally expand.
Right, thermal expansion.
Combine that elevated sea level with high tide flooding, and then layer on the relentless storm surges driven by the altered jet stream.
That sounds like a disaster for the coast.
It is. That combination can easily overwhelm existing coastal infrastructure.
Now wait. I was reading through the NOAA data, and there is a seemingly contradictory fact here that I really need you to explain.
Okay, let's hear it.
If the planet is hotter, and the Pacific is supercharging all these storms, why is NOAA predicting a below-normal 2026 Atlantic hurricane season?
It's a great question.
It just feels completely backward. Shouldn't more heat equal more hurricanes everywhere?
It does feel like a paradox, but it's a brilliant example of atmospheric physics in action. It's a mechanical issue called vertical wind shear.
Okay. What is wind shear and how does it kill a hurricane?
Remember that massive column of rising hot air in the eastern Pacific we just talked about?
The one shifting the jet streams.
Right. When that air hits the top of the troposphere, it has to go somewhere. It spreads out and blasts eastward, creating very fast, rapidly shifting upper-level winds across the Atlantic Ocean.
Fast winds high up in the atmosphere.
Exactly. Now, think of a developing Atlantic hurricane like a delicate, towering chimney.
A chimney. Okay.
For a hurricane to build its engine, it needs calm upper-level winds so it can stand straight up and efficiently pull moisture from the ocean surface high into the sky.
Ah, so it needs perfect vertical stability.
Right. But those fast upper-level winds blowing over from the Pacific act like a giant invisible buzzsaw.
Oh, I see. They create the wind shear.
Yes. As the Atlantic storm tries to build its chimney, the wind shear mechanically rips the top off the storm before it can organize into a mature hurricane.
It just decapitates the storm.
Exactly. So, paradoxically, the intense heat and rising air in the Pacific mechanically destroy the storms in the Atlantic.
That is wild. The atmosphere is just so incredibly interconnected.
It's all one big machine.
And what about the physical ocean itself? Not the air above it, but the water.
That is perhaps the most concerning long-term impact in all of this.
Really? Why is that?
Because the surface water of the Pacific is so unusually warm, it creates a thermal cap.
A cap.
Yeah, it suppresses a process called ocean upwelling. Normally, cold, dense, nutrient-rich, deep water rises to the surface. That upwelling is the foundation of the marine food web.
But the hot surface water essentially traps the cold water deep down.
Exactly. It's too buoyant. Without those nutrients reaching the surface, and with the water temperature spiking, we see widespread marine heat waves.
Which affects everything living there.
This leads directly to severe coral bleaching on a global scale, fundamentally threatening oceanic ecosystems.
Okay, so we've established the global physics, the jet streams, the wind shear, the upwelling. But if you're a listener mapping out your year, what does this actually look like month by month?
That's the practical side of all this.
Right, because the sources provide a very specific timeline for how this unfolds over the next year.
Yes, and it's crucial to view this as a multi-month roadmap, rather than a sudden overnight disaster. The impact rolls out in distinct phases.
All right, let's go through them. Phase 1 is happening from May to October 2026. The sources call this the wet or transition season.
Right.
Now, I have to ask about a discrepancy here. We just established that El Niño pulls the moisture away and causes severe droughts in the Western Pacific.
We did.
Yet, the forecast models for the region still project 9 to 17 tropical cyclones moving through before the end of this year.
I know, it sounds confusing.
How can you have a severe drought and up to 17 cyclones happening in the same season?
It's a great question, and it highlights a very common misconception. Counterintuitively, an El Niño transitioning in doesn't mean the rain just instantly shuts off.
Oh, it doesn't.
No. During phase 1, you are still going to see tropical storms and monsoon rains.
Okay, so what changes?
The hallmark of phase 1 isn't absolute dryness, it's extreme inconsistency.
Inconsistency.
Yeah, you might see a massive, intense storm dump and overwhelming amount of rain in 2 days, but it will be immediately followed by a prolonged, unusually dry, blisteringly hot stretch for weeks.
Just totally chaotic weather.
Exactly. The primary threat during this phase isn't just the storms, it's the dangerous heat index on those clear days, because the global baseline is already so hot.
Which explains why local agencies are fundamentally changing how they warn people.
They have to adapt.
I was looking at Dos Pegasus protocols. They are hosting their Typhoon and Flood Awareness Week this June. But more importantly, they recently implemented a modified tropical cyclone warning signal system, the TCWS.
Right, a major overhaul.
They even had to revise their official definition for a super typhoon.
And that ties directly back to our baseline discussion. Because the ocean has so much more baseline thermal energy, when storms do form, they have a much higher energy ceiling.
They can get way stronger, way faster.
Yes, they can undergo rapid intensification, exploding in strength in a matter of hours. The old warning categories simply didn't account for the sheer explosive wind speeds or the erratic behavior we see now.
The old system was literally breaking.
Exactly. Local agencies realize that during these inconsistent transition phases, warning systems need to capture sudden hyperintensification, not just predict total rainfall.
That makes a lot of sense. So that takes us to phase 2, November 2026 to January 2027. This is the peak.
Yes, this is when the Artemis liftoff completes, and the El Niño reaches its maximum strength in the Central Pacific.
So what happens then?
Historically, this phase acts as a hard stop. It suppresses the tail end of the typhoon season in the western Pacific.
Oh, so the storms finally turn off.
Right. Any late-year storms that manage to form tend to either completely miss land because the steering currents have shifted, or they simply lack the atmospheric moisture to dump their typical levels of rain.
Which sets up phase 3 in early 2027. The sources call this the dry season backlash.
And it is a severe backlash.
And if I'm putting the pieces together, because phase 2 just suppressed all the rain at the end of the year, it means we are basically starting the dry season running on empty.
You've hit the nail on the head. That is the critical compounding impact.
Wow.
The vital water reservoirs rely on those late-year storms to fill up. Because the rains were suppressed, the reservoirs aren't replenished.
They just stay low.
So when the natural dry season arrives in early 2027, the lack of stored water amplifies into a severe, localized agricultural drought.
Which is devastating for food supplies.
It is. You see significant water stress for urban areas, too.
Yeah.
The worst impacts on the ground actually lag months behind the peak of the El Niño itself.
So understanding this timeline, phase 1 inconsistency, phase 2 suppression, phase 3 backlash, it isn't meant to scare anyone.
Not at all.
It's actually a playbook. If we have this multi-month buffer, these sources aren't just telling us to panic. There has to be a way we actually handle this.
There absolutely is.
If you are listening right now today, what are the practical steps you should be taking?
The advantage of atmospheric physics is that it gives us time. There are 3 major practical adaptations you can make immediately.
Okay, what's number 1?
First, manage your power and heat expectations. With higher than normal temperatures forecast from May through October, cooling systems are going to run much longer and much harder.
So prioritize home ventilation or energy-saving habits now.
Exactly.
Don't wait until August to realize your air conditioner is inefficient and your power bill has tripled.
Precisely. You have to get ahead of the prolonged cooling needs. Second, and perhaps the hardest psychologically, is water conservation.
Because it's hard to think about when it's still raining.
Right now, in May 2026, depending on where you live, it might be raining. Tap water might feel abundant. But as we just discussed, a massive reservoir deficit is already baked into the timeline for early 2027.
It's hard to save water when it's raining outside, but adopting simple water-saving habits today is actually about banking resources to prevent pressure drops and rationing down the line.
Yes. You have to manage the resource for the forecast, not for the weather outside today.
That's a great way to frame it. And the third step.
The final step is a golden rule for modern meteorology. Watch official skies.
Stop doom scrolling.
Exactly. Avoid the viral social media accounts that are just hunting for engagement by hyping up the super El Niño apocalypse.
So if people want the real data, where should they look?
The WMO's World Weather Information Service is an excellent hub.
Okay, good to know.
It aggregates official observations and forecasts directly supplied by national meteorological and hydrological services worldwide. You want your data coming from the scientists who actually calibrate the instruments, not the influencers monitoring algorithms.
Here's where it gets really interesting. We started this deep dive talking about a weather anomaly.
We did.
We tracked this massive Artemis liftoff of heat in the Pacific, powered by that reversed oceanic treadmill.
That sloshing of hot water.
Right. We broke down how that heat alters global jet streams, creates atmospheric buzzsaws that kill Atlantic hurricanes, threatens deep-sea coral, and fundamentally dictates when you need to run your air conditioner and conserve your shower water over the next 12 months.
It is a phenomenal cascading chain of physics.
Yeah.
I mean, a wind anomaly at the equator eventually dictates the water pressure in your home.
It really is wild. But I want to leave you with a final lingering question to ponder long after this deep dive is over.
Okay, let's hear it.
We've always viewed El Niño as a temporary cyclical phase. It comes, it shifts the jet streams, causes a year of disruption, and eventually passes, returning us to a normal baseline.
That's how it's always worked.
But considering our unprecedented, record-breaking global baseline temperatures, what happens if these extreme temperature anomalies stop being cyclical events?
Oh, wow.
What happens if they start blending into a permanent state of the ocean?
That is the exact question keeping atmospheric scientists awake at night. It tests the absolute limits of our adaptability.
If the Artemis liftoff becomes the new normal, how will our global infrastructure, our agriculture, and our daily lives need to fundamentally evolve to survive a world where that oceanic treadmill gets stuck in reverse and the Pacific simply never cools down?